Thank you. Now, not very many people have had an opportunity to see what will be demonstrated in the laboratory. The word plutonium itself isn't exactly a household word. We don't use it too often. But on the other hand, the discovery of this new element was of vital importance to every one of us because it ushered in an entirely new field of science, the field of atomic energy. Now, before going on with our plutonium story, I'd like to tell you a little bit about our guest scientist. Our guest this evening is Dr. Glenn T. Seaborg, professor of chemistry at the University of California. And Dr. Seaborg was one of the leaders of a team of scientists who in 1940 made this discovery of plutonium. Now, for that work, in addition to other fundamental research in the field of chemistry, he was awarded the Nobel Prize in Chemistry in 1951. So we're very glad to have him with us this evening. And welcome to Science in Action, Dr. Seaborg.
Thank you, Earl. I'm glad to be here to tell you about plutonium. I'm also glad that you said team of scientists, because the discovery of plutonium, like that of the other transuranium elements, was the work of a number of scientists.
Of course, Dr. Seaborg, all specialists have their own vocabularies, and I notice you start right off with a word there that sort of stops me, and that's transuranium. How would you go about defining transuranium?
Well, I'll explain that. I think I can do that best with the help of this periodic chart back here. In the periodic chart, as you know, the elements are arranged essentially in the order of their increasing weights. That is, at the top, hydrogen number 1 is the lightest. And then we proceed through the elements according to the increasing weights. Now, if I may point out a few examples, tin, number 50, and gold, number 79, and then on up to uranium, number 92. Now, a number of scientists had thought that there might be elements beyond uranium, but none had been discovered before 1940. So, in a sense, our story tonight begins with 1940, because in that year, number 93, neptunium, was identified, and a little later that year, plutonium, number 94, was identified. Uranium is the heaviest naturally occurring element, and the elements beyond uranium are all made from uranium. They're made from uranium, and they're beyond uranium, and hence the term transuranium.
Well, of this transuranium group, we couldn't go out prospecting and find any of these, could we?
No, they're all man-made. They're all synthetic.
Man-made and in the laboratory.
The entire group from here to here, the transuranium group.
Well, a short time ago, we visited Dr. Seaborg at his laboratory in Berkeley. And while there, we went with him to the cyclotron, where a number of scientists are working on these transuranium elements. We had the opportunity of meeting Dr. Ernest O. Lawrence, the director of the radiation laboratory, and Dr. Donald Cooksey, assistant director. Dr. Lawrence invented the cyclotron, for which he was awarded the Nobel Prize in 1939. Here he is with his first model. Now, at the 60-inch cyclotron in Crocker Laboratory, Dr. Seaborg here is talking to Dr. Edwin M. McMillan. Incidentally, Dr. McMillan was one of the discoverers of neptunium. Didn't you say, Dr. Seaborg?
Yes, early in 1940, Dr. McMillan and P.H. Abelson first identified the element neptunium. Dr. McMillan began the search for element 94, plutonium, but he was called away to other government service. Then we went on and finished Dr. McMillan's work, which led to the successful identification of plutonium later on.
Dr. McMillan's also a Nobel Prize winner, isn't he?
Yes, he and I won the awards for our work on plutonium and other research.
Well, here's a picture I know is very dear to your heart, the room in Gilman Hall where plutonium was discovered. That was Dr. Wendell Latimer that was with you, wasn't it?
Yes. The gentleman with me is Dr. Wendell Latimer, who was Dean of the College of Chemistry at the time of the discovery.
Well, when did you actually discover plutonium, Dr. Seaborg?
Well, the discovery, it's hard to say exactly when it happened, because a discovery of this sort is a progressive sort of thing. I would say that it began in the fall of 1940 and culminated in about March 1941.
Oh, I see. Well, now, before we leave the periodic table, I'd like to point out some of these other elements. Here's number 95, americium, another 96, curium, number 97, berkelium, number 98, californium. But here's some blank spaces, 99, 100, 101, 102, 103. What about these, Dr. Seaborg?
Well, it shouldn't be too hard to go up to 100, especially since a number of men like Professor Perlman at the University of California and others have charted the properties. But to go beyond 100 is going to be tough because of the high rate of radioactive decay, so making it possible that they will have disappeared before we can identify them.
That radioactivity is important. All of these are radioactive here, all this transuranium group?
Yes, the important things about them, to point out, they're man-made and they undergo radioactive decay.
Oh, I see.
Earl, if you step over here, we'll show you a little bit about this radioactivity.
I'd like to introduce another member of the team of scientists who are working on the transuranium elements, Mr. Albert Ghiorso. What are you doing with all this equipment here, Al?
I've been checking the equipment, Earl, and I think everything's all set for our experiments this evening.
Do you have a 50-cent piece, Earl?
Well, I have one here someplace. Let's see. I'll go you a better one. Here's a silver dollar. How's that?
All right. We'll use this to demonstrate radioactivity. We have here a Geiger counter, which is inside of this lead shield, which shields it from the cosmic rays, and that's hooked up to the recorder here. Now, I'll put this silver dollar under the counter, and if it's radioactive, it would click. But, of course, an ordinary silver dollar is not radioactive. The only clicks you hear on the recorder are due to the cosmic ray background. Now we'll irradiate this with neutrons to see if we can illustrate the making of a radioactive substance.
I see. You have a source here, and you put that under the...
That's right. There's a source of neutrons in this paraffin cylinder here. And the neutrons go through the silver dollar. Some of them are captured by the silver, and this makes the silver radioactive, as we'll see in a moment.
About how long will that take now?
Well, I think it is radioactive enough to measure by now.
Fine.
Yes. Now that's illustrates the radioactivity of the silver, you see.
So that much changed just by putting it in front of that
That's right,
source.
by the capture of the neutrons.
Well, it's very obvious that my silver dollar has become radioactive, but how does this same procedure apply now in the making of plutonium?
Well, that's a little complicated. If you'll come back to the chart over here, why, I'll try to explain that.
Oh, fine.
What is involved here is a change in element due to the radioactivity.
Yes.
On this chart here, we see a representation of the hydrogen nucleus, which has one proton in it. And then as we go up to a more complicated element, we have the tin nucleus, which has 50 protons in it and has an atomic number of 50.
Yes.
And going up to a larger nucleus, we have 79 protons in gold. Gold has an atomic number of 79. And then on up to uranium that we spoke of before, 92 protons, an atomic number of 92. This defines the element, this atomic number. Now, there are also neutrons in the nucleus. In the case of uranium, the common uranium with mass 238 has, in addition to 92 protons, 146 neutrons. You see, 92 plus 146 makes 238.
Oh, that's the way you get that U-238.
That's right. Well, now, if, as we did in the case of silver, we bombard the uranium-238 with neutrons, the uranium captures a neutron. We can write that this way to depict the reaction, you see.
Oh, yeah.
And then we have 92 protons still, but 147 neutrons. Now, this is not a natural form of uranium that has too many neutrons. And one of the neutrons changes to a proton, as depicted in this reaction here. That is, we have 92 protons. One of the neutrons changes to a proton.
I see.
That makes 93 protons, and this occurs on the average in about a half an hour and makes the element neptunium with the atomic number 93. And this also changes by a neutron changing into a proton. 93 protons become 94 protons, and we have the element plutonium.
Well, that's the way it works. Well,
Yes, and now we're going to try to do that in the laboratory here also.
Fine.
We've been irradiating some uranium here for about a half an hour, and this should illustrate the change of uranium into the radioactive form. Al, is the sample ready, do you think?
I think our sample's been irradiated long enough. Let's take the apparatus apart and see what it consists of. This is the neutron source. There are as many neutrons emitted by this source as that from a 1-gram quantity of Madame Curie's famous radium mixed with beryllium. The neutrons are slowed down by the paraffin here so that they are more readily captured by the uranium. And here is our sample of uranium, which has been bombarded for the last hour.
Yeah, now this is the sample that we think has captured neutrons and become radioactive. Now, in order to illustrate this graphically, I have a sample here of ordinary uranium that hasn't been irradiated and which shouldn't be particularly radioactive, you see. And it doesn't increase the background particularly.
Now, what will happen with this?
Now, this should be radioactive, much like the silver was, because it has captured the neutrons, and
that's
as you see, the experiment works.
Yes.
And the uranium has turned into the U-239 with the
It's going
conversion
to
of neutrons.
neptunium and then to plutonium.
Yes. Of course, we don't have very much plutonium in the sample yet, because, as I indicated, it takes some time for the uranium to change to the neptunium, and the neptunium to change to plutonium.
Well, now, the equipment that you people used in the original discovery of plutonium was a lot more complicated than this simple demonstration we set up here in the laboratory.
Yes, it was a great deal more complex. It was too large, of course, to get into a laboratory of this size. For example, it involved the 60-inch cyclotron in the Crocker Laboratory at the University of California to furnish the neutrons for the irradiation. Now, I think that we have a picture of Dr. Joseph G. Hamilton, director of the Crocker Laboratory, and his associate, Bernard Rossi.
They've been very instrumental in this work, haven't they?
Yes. That's a picture of Dr. Hamilton and Mr. Rossi at the control desk of the cyclotron. While using that tremendous source of energy, it was possible to carry on the experiments I've described and make the neutron irradiation, which led to the identification of the new element.
Well, now that we've seen how plutonium is made from uranium, then what is the next step?
Well, although plutonium was an unknown quantity in 1940, there were certain expected traits that we decided we could look for in order to demonstrate that a new element had been produced.
In other words, what you had to do was prove that what you suspected to be the case was actually the case.
Yes, and that's exactly what we did. That is, in 1940, Dr. Joseph W. Kennedy and Dr. Arthur C. Wall, who are now at Washington University in St. Louis, collaborated with me in the chemical identification of the plutonium that had been produced in this way. Now, we're going to try to perform one of the experiments that Kennedy and Wall and I did in 1940 and 41 to make this chemical identification. In these two tubes, we have plutonium. In this tube, in the reduced state, and in that tube, in the oxidized state. And Al has already added some lanthanum carrier, and he's now adding the hydrofluoric acid to precipitate the lanthanum fluoride in each case. Now, next he's going to put them into the centrifuge to separate the precipitate from the solution.
Of course, the centrifuge speeds up things quite a bit. It throws the heavier material to the outside, or to the bottom of the tube.
That's right. That's right. And what we're going to look for, as was the case in the original experiment, is to see where the radioactive plutonium is. Now, if the experiment has succeeded, after Al pours off the solution so that we can separate the solution from the precipitate, in the case of the reduced solution, the activity should remain in the precipitate and not show up on the Geiger counter when he puts
There's
the solution
nothing showing at all. In other words, it's inactive.
That's right, it's inactive. Now, in the case of the oxidized solution, when he separates the precipitate from the solution above it, the activity should remain in the solution. That is, you should get the clicking of the Geiger counter.
There, that certainly demonstrates it.
That's an essential reproduction of the experiment that chemically identified plutonium.
In other words, this was your final test, the one thing that clinched it and told you that you had something that was entirely different from every other known element.
That's right. That's right. We knew then, although we didn't have enough plutonium to see it in our test tubes, that the new element had been formed.
Now, before we go on, let's see if we have the highlights of this plutonium story. First of all, Dr. Seaborg has told us about the transuranium elements. These are the elements in this part of the periodic table. We've heard how they are made from uranium, and we've seen an actual small amount of plutonium made in the laboratory. We've also seen how Dr. Seaborg and his colleagues were able to prove conclusively that what they had was plutonium and not some other element. Now, Dr. Seaborg, what do we proceed to now in the next step?
Well, the reason that plutonium has become important is because it undergoes fission.
Well, that fission is certainly something that we should remember.
Yes, it's an important reaction because the fission of atoms creates atomic energy. Now, very briefly, when an atom splits apart, when a neutron strikes it, large amounts of energy are released. Of course, not all atoms do this. We had reason to suspect that plutonium-239 would do it, just like U-235 does.
Yes.
And once we'd found plutonium-239, it was our job to try to demonstrate whether it underwent fission. Now, Dr. Amelia Segre and Dr. Kennedy and Dr. Wall and I did this experiment by exposing plutonium-239 to slow neutrons, and we found that it fissioned just like U-235. That's Dr. Segre there with me.
Well, now, can you repeat that famous experiment for us?
Well, we're going to try, Earl. We'll even use the same counter that was built by Dr. Clyde Wiegand at the University of California and used by Dr. Kennedy when he went around the country back in 1941 trying to convince the people involved that plutonium underwent the fission reaction and was worth producing in quantity if possible. Al will show you what the fission looks like on the oscilloscope attached to the counter. We're going to use uranium-235 because that's easier to do tonight and because the effect is essentially the same.
This is the neutron source that we used before. The ionization chamber containing a small amount of U-235 is in here, and here's the oscilloscope on which we will see the radioactivity. These small pips that you see here are due to the natural radioactivity of the U-235. Now watch closely while I add the neutrons put them near the counter.
Say, that's certainly a difference there. That is due to the fission, then. We're getting these extra pips that come up there.
Yes, those peaks are due to the fission reaction. The small peaks that you saw first were due to the radioactivity of the uranium, and then corresponding to about 4 million electron volts. And then the big kicks are the big flashes are the fission flashes corresponding to about 200 million electron volts of energy. So you see there's a lot of energy available here.
200 million volts. You know, that's so much it's hard to visualize that. Now, Dr. Seaborg, you and your colleagues had proved in 1941, of course, that plutonium-239 was fissionable, but beyond that you had a considerable amount of work to do.
That's right. Up until this time we hadn't even seen any plutonium, and it was necessary to work out the chemical process in connection with its industrial manufacture. So the next step was to produce it in quantities where this process could be worked out. Dr. Stanley G. Thompson, who is with me at the radiation laboratory, is largely responsible for the process used. We used the methods of ultramicrochemistry, which were developed by Professors Paul Kirk and Professor Burris Cunningham at the University of California. I wonder whether you'd like to see some of the equipment that's used in this science of investigation of extremely small amounts of material.
I certainly would. In fact, I was looking at this microbalance a little while ago, and this is the most fantastic instrument I've ever seen. It weighs materials down to 1/1000th of an ounce. That's really getting down there.
Yes. And another thing that's just as interesting are these small tubes here, micro cones, in which the solution chemistry is carried out. That is, the chemistry is worked out with volumes as small as 1 drop of liquid in these microcones.
Those are extremely small. Now, speaking of small quantities, Dr. Seaborg, I know you don't usually carry samples of plutonium around with you, but since you did bring some over to the laboratory this evening, I'm wondering if we could see it.
Well, we can, if Al can rig up the microscope here. This little sample of plutonium has a certain historic value because it contains the first visible amount of plutonium that was made by man. This was produced in the Chicago Metallurgical Laboratory and identified by Dr. Burris Cunningham and Dr. Louis B. Werner.
I see, and this is the first bit that was ever seen by anyone. You know, that is really something to be able to see that.
It was first isolated by them in amounts large enough to see.
Yes, that's really very good.
Well, now, Earl, Al has rigged up a lively sort of demonstration over here that shows us what a chain reaction is. Over at the other part of the laboratory, you'll see in a moment a series of mouse traps, which are all set. They represent these mouse traps represent the atoms of U-235 and plutonium-239. And the corks, which are placed on the mouse traps, represent the neutrons. Now, if we drop a neutron into the setup, it will make one of the atoms fission. That is, the cork will spring one of the mouse traps. The sprung mouse trap will release two more corks, or neutrons, which will cause more fissions to take place. Al has rigged up some lights to the mouse traps so that we'll be able to watch the progress of the chain reaction. Al, why don't you start it off?
Boy, look at that. Those lights came on there, too. You know, that is a most graphic demonstration that I've ever seen of what a chain reaction actually is. Now, Dr. Seaborg, there's one thing that I want to ask you about, and I know that you must get this question quite often. What is the future of atomic energy?
Well, these large amounts of energy that we've been talking about have the possibility of being released in a slow, controlled fashion, as well as in a hurry this way. To illustrate the amounts of energy involved, I brought a harmless sample of uranium along. This is about 1 pound of uranium metal, which, if all of the atoms, the nuclei, underwent fission via the plutonium, as we've discussed tonight, would release an energy corresponding to about 10 million kilowatt hours.
10 million?
Enough to run, well, a few pounds a day would run a city of the size of San Francisco. But I want to caution you that there is a lot of research and engineering work to be done before this can come to pass. The Atomic Energy Commission, in their various laboratories, are carrying on an infancy program, which I believe will be successful. But, as I say, it'll take some time.
Yes.
People may be interested in the economics of the process. Here, we're not ready to give an answer. We don't know whether it'll be as economical as other sources of energy. But even if it isn't, being such a concentrated source of energy, it has uses that can't be equaled by other sources and therefore will be of value.
Well, we'll certainly look forward to that. And Dr. Seaborg, I want to thank both you and Mr. Ghiorso for being with us on Science and Action. It's been a most instructing and entertaining period.
It was a pleasure.
Our animal of the week is a murine possum, and it comes from Veracruz province in Mexico at a place called Minatitlan. And it was brought to Science and Action by a friend of ours, Mr. Sterling Bunnell, who is here in the laboratory to demonstrate this little fellow. He lives in an old sock, and we'll see if we can... oh, there he comes peeking out. Nice little fellow. He's sometimes a little bit frisky, though, and we have to be very careful. Now, you remember the opossums normally have... oh, now we'll boost him over in the center here. And, Sterling, would you show us your magic technique with this little fellow so that we can see how he should be picked up? I'm not as familiar with him as you are. Oh, there he comes up. Cute little rascal. Maybe we can get him around to the front here so that we can see what those big eyes look like. Really a cute little rascal. And this is a full-grown possum, isn't it, Sterling?
Yes, that's as big as they get.
How did you happen to catch him?
Well, I was on a vacation down there, and I was curious to see what sort of small animals lived in the forest, so I set some traps, and this is what I caught.
Well, that's a cute little fellow, and it's an adult male, is that right?
Yeah, he has a prehensile tail, as you see, and an opposable big toe on his hind foot.
Well, he seems to be a bit disturbed there. I hope he likes your coat. He seems to. Yeah. I'll put him right back down in his cage there again. Hey, that's a wonderful animal, and you're planning to keep this and study the animal.
Well, yes. I don't believe these animals are very well known in this country.
Yes. And this one does not have a pouch. In other words, the females just carry the young on the underside of the body?
Yes, that's right. That's true of all the murine opossums in South America.
A little bit different from the possum that we have in this country.
Oh, quite.
He's a cute little fellow. Well, Sterling, I want to tell you that we certainly appreciate having you bring this little rascal from far off Veracruz to Science and Action, and we hope to see him again sometime.
All right.
Now, I have something down here that will interest you. It's a star performer on our next program. I'm going to take him out and put him out in the center of the floor here. very carefully, and I think when he's out there, you'll then know what our program is going to be about. Handle it very carefully. Big civic rattlesnake. Our next program is on rattlesnakes. Our guest will be Dr. Lawrence M. Klauber of San Diego, the world's authority on rattlesnakes. This is a big fellow, just brought in just recently. We'll see if we can pin him here. He's a little bit frisky. Hold him down there very carefully. And reach down. You can see he's a good-sized fellow with a number of rattles here on the tail. Well, that's rattlesnakes then for our next program. We hope you'll plan to be with us then. Thanks a lot.
You have just seen another in the fascinating television series, Science in Action. Science in Action is produced by the California Academy of Sciences under the supervision of Dr. Robert C. Miller.